Bismillahirrahmanirrahim. Assalamu alaikum. We will study plasma physics 2. Course code is PHYS4131. We start with chapter 1, waves in plasma. First of all, introduction. Plasma is a complex fluid that supports many plasma wave modes. Wave phenomena are important for heating plasmas, to measure their instabilities, and diagnostics. In vacuum, there is only one wave mode, the electromagnetic wave, with omega over k is equal to c and having electric and magnetic field components perpendicular to k. In air, both sound waves and electromagnetic waves propagate, and in plasma, both electrostatic waves and electromagnetic waves will propagate. How we represent waves in plasmas? Any sinusoidally oscillating quantity, say the density, can be represented as n is equal to n naught e to power iota k dot r minus omega t, where k dot r is equal to kx x plus ky y plus kz z in Cartesian coordinates. We can write x, for example, in one dimension, then density can be written as n is equal to n naught e to power iota kx minus omega t. The density of the sinusoidal oscillations to be measured is, the real part can be written as Re of n is equal to n bar cos of kx minus omega t. The term in bracket is called phase. The term kx minus omega t is called phase. How we can calculate the phase velocity is that if we differentiate the term kx minus omega t with respect to time and put it equal to 0, then we can easily find the phase velocity. But to find phase velocity, we should remember or recall the phase definition of the phase velocity, which is the velocity on the wave of a point of constant phase. If we have an observation phase, then phi naught is equal to kx minus omega t. If one moves with the phase, d phi naught over dt is equal to 0 in phi coordinates, then in x coordinate d by dt kx minus omega t is equal to 0. Taking time derivative, we can get phase velocity is equal to omega over k. The phase velocity is the velocity on the wave of a point of constant phase. Let's consider an oscillating quantity in the wave, say the electric field E. Since we have already chosen the phase of n to be 0, we must allow electric field E to have a different phase, which we represent here as delta. So we have E is equal to E cos of kx minus omega t plus delta, or we can write it as exponential function, and E is equal to e to power iota kx minus omega t plus delta. And if we separate the terms, then we can merge e to power iota delta into electric field magnitude. So we get a complex function EC is equal to E exponential to power iota delta, which can be written as E cos delta plus iota E sin delta, and we can write it as tangent of delta is equal to imaginary part of EC over real part of EC. In general, electric field component in general electric field is equal to E to power iota kx minus omega t. In other words, EC is a complex amplitude because if there are many waves in a medium and they have on phase, then we get the complex amplitude, which we represent here as EC. Our next topic is group velocity. Information is usually encoded on a carrier wave as either a modulation of its phase or amplitude. A simple amplitude modulated wave can be constructed by combining two carriers of slightly different frequency, omega minus delta omega and omega plus delta omega. The resulting pattern or beat travels at the group velocity. For example, if we have two waves E1 and E2, then the resultant will be E, which is equal to E1 plus E2. Putting value of E1 and E2, we get E is equal to 2 E naught cos of delta kx minus delta omega t cos of kx minus omega t. The group velocity of a wave is the velocity with which the overall envelope shape of the wave's amplitude, known as the modulation or envelope of the wave, propagates through space. The formula of group velocity is Vg is equal to d omega over dk, which is less than c speed of light. Next is plasma oscillations. As we know that plasma consists of electrons and ions, and overall plasma is a neutral, and if the electrons in plasma are displaced from a uniform background of ions, electric fields will be built in such a direction as to restore the neutrality of the plasma by pulling the electrons back to their original positions. Because of their inertia, the electrons will overshoot and starts oscillation around their equilibrium positions with a characteristic frequency known as the plasma frequency. Assumptions or conditions are: there is no magnetic field, there are no thermal motions, i.e. the product of Boltzmann constant K and temperature will be equal to 0. The ions are fixed in space in a uniform distribution. The plasma is infinite in extent. The electron motions occur only in the x direction. Applying all these conditions, we therefore get no fluctuating magnetic field. This is an electrostatic oscillation. Electrostatic oscillations occur when there are no fluctuating magnetic fields. We can write the electron equation of motion and continuity equation as mne into partial ve over partial t plus ve dot del into ve is equal to minus E N E electric field capital E, and also the continuity equation partial Ne over partial T plus del dot NeVe is equal to 0. We already known these equations in our plasma physics 1 course. We can also use Poisson equation to find electric field. The expression for the Poisson's equation is here written as epsilon naught del dot E is equal to E into Ni minus Ne. We know that Ne is the electron density, Ve is the velocity of electrons, and density of ions is represented as Ni. Now we simplify these three equations. We separate the dependent variables into two parts, an equilibrium part indicated by a subscript 0 and a small perturbation part indicated by a subscript 1. Therefore, Ne will be equal to N0 N0 or N0 plus N1. Ve is equal to V0 plus V1. E is equal to E0 plus E1. Using these values in above three equations, we get simplified expressions where we have dropped high order perturbation terms and assumed a uniform neutral plasma at equilibrium. The oscillating quantities are assumed to behave sinusoidally. Therefore, the expression for V1 will be equal to V1 exponential to power iota kx minus omega t x hat. N1 will be equal to N1 exponential to power iota kx minus omega t. Electric field E will be equal to E exponential to power iota kx minus omega t x hat. To further simplify, we use partial of partial t equal to minus iota omega and the differential operator delta equal to iota k. Using these values in above equations, we obtain three different equations. Then we will simplify them by eliminating N1 and E1, which gives us plasma frequency omega p square is equal to N naught E square over epsilon naught m to power square root, or 1 over 2. This frequency or plasma frequency depends on the plasma density, which is one of the fundamental parameters of a plasma. Because of the smallness of mass, the plasma frequency is usually very high. For instance, in plasma of density n equal to 10 to power 18 m minus 3, we have Fp is equal to omega p over 2 pi, approximately equal to 9 gigahertz. In particular, omega does not depend on the value of k, so Vg or group velocity is equal to d omega over dk will be equal to 0. The disturbance does not propagate. They can be pictured as independent oscillators. We can also describe plasma oscillations as rapid oscillations of the electron density in conducting media such as plasmas or metals in the ultraviolet region. The oscillations can be described as an instability in the dielectric function of a free electron gas. Our next topic is electron plasma waves. There is another effect that can cause plasma oscillations to propagate, and that is thermal motion. Electrons streaming into adjacent layers of plasma with their thermal velocities will carry information about what is happening in the oscillation region. Plasma oscillations can be properly called a plasma wave. We can easily treat this effect by adding a term differential of momentum p del p e to the equation of motion. The equation 1 of last topic. For one dimension, capital N can be equal to 1, gamma is equal to n plus 2 over n is equal to 3. Using all values and simplifying, we get differential PE is equal to 3 kte partial n1 over partial x hat, and the linearized equation of motion is m n naught partial v1 over partial t is equal to minus e n naught e1 minus 3 kte partial n1 over partial x. We simplify this equation by putting value of partial t equal to iota omega, and partial of partial x is equal to iota k. Further, we replace the values of e1 and n1 in the above equation. Then we simplify this equation by taking common v1. Then v1 will cancel on both sides. Then we obtain the frequency omega square is equal to omega p square plus 3 by 2 k square v thermal square, where v thermal square is equal to 2 kte over m is the thermal velocity. The frequency now depend on value of k, and the group velocity is finite here. Group velocity can be calculated as Vg is equal to d omega over dk is equal to 3 by 2 k over omega. Vth square is equal to 3 by 2 Vth square over v phi, as the phase velocity is equal to omega over k. Therefore, we replace k over omega in this expression with phase velocity term v phi. Our next topic is sound waves. Let's review theory of sound waves in ordinary air. We know that sound waves travels as compressions and rarefactions. We take two equations, or we have two equations for two variables, density and velocity. First one is the Navier-Stokes equation, which is the partial differential equation that describes the flow of incompressible fluids. The equation is generalization of the equation devised by Euler in the 18th century to describe the flow of incompressible and frictionless fluids. This equation is a generalization of the equation devised by Euler in the 18th century to describe the flow of incompressible and frictionless fluids. The second one is the equation of continuity. For stationary equilibrium, we have rho naught of p naught is equal to v is equal to 0. Using all these values in above equation, we get minus iota omega rho naught v1 is equal to minus gamma p naught over rho naught iota k rho 1, cancelling similar terms on both sides, and further simplifying this, we are left with minus omega rho 1 plus rho naught k dot v1 is equal to 0, and further simplifying we get minus omega rho naught v1 is equal to minus gamma p naught k square over omega v1, and the final equation for the speed of sound in a neutral gas will be equal to Vph, or phase velocity, is equal to omega over k is equal to gamma p naught over rho naught power 1 over 2. Then using values of p naught and rho naught, we get gamma kt over m to power 1 over 2, which is equal to Cs, the speed of sound in a neutral gas, or this term is equal to Vg, or the group velocity. This is the expression for the velocity Cs of sound waves in a neutral gas. The waves are pressure waves propagating from one layer to the next by collisions among the air molecules. In a plasma with no neutrals and few collisions, an analogous phenomenon occurs. This is called an ion acoustic wave, or simply an ion wave. Next we will study ion waves. Ions can transmit vibrations to each other in the absence of collisions because of their charge. Acoustic waves can occur through the intermediary of electric field. Since the motion of massive ions will be involved, these will be low frequency collisions, and we can use the plasma approximation, that is, ions density will be equal to electron density, and which is equal to density, overall density. Instead of Poisson's equation, we use n is equal to ni is equal to ne instead of Poisson's equation. Then the ion fluid equation in the absence of a magnetic field can be written as mn partial vi over partial t plus vi dot differential operator into vi is equal to En product of with electric field vector minus differential of momentum operator p is minus del p, which is equal to minus En del phi minus gamma I kti differential of density n. Linearizing and assuming plane waves, we have equation minus iota omega m n n naught v1 vi1 is equal to minus En naught iota k phi 1 minus gamma I kti iota k n1. Since ions are heavy as compared to electrons, so we assume that m is equal to 0. The balance of forces on electrons requires that Ne equal to n naught exponential of E phi 1 over kte, or we can also write it as n naught into 1 plus E phi 1 over kte plus so on. The perturbation in density of electrons and therefore of ions is then n1 equal to n naught E phi 1 over kte. The linearized ion equation of continuity will be written as iota omega n1 equal to n naught iota k v I1. Let's substitute the value of phi 1 and n1 in above equation. Then we will arrange this new expression in terms of vi1 then we get iota omega capital N n naught vi1 equal to E n naught iota k kt e over E n naught plus gamma I kti iota k into n naught iota k vi1 over iota omega. We further simplify this equation and we rearrange this expression and we get omega square is equal to k square into kte over capital M plus gamma I kti over capital M. We get dispersion relation for ionocaustic waves, which is given by omega over k is equal to kte plus gamma I kti over capital M to power 1 over 2, which is equivalent to the sound speed in a plasma, and we represent it with Vs. We must note that since the ions suffer one-dimensional compressions in the plane waves, gamma I will be equal to 3. The electrons move so fast relative to these waves that they have time to equalize their temperature everywhere. Therefore, the electrons are isothermal and gamma I will be equal to 1. Also, the group velocity will be equal to the phase velocity. When kti approaches to 0, ion waves still exist. We must note that ion waves will exist also when kti approaches to 0. Our next topic is validity of the plasma approximation. While driving the velocity of ion waves, we have used the neutrality conditions. Ni is equal to Ne, or the density of ions is equal to density of ions is Ni, which is equal to electron density Ne, while allowing electric field E to be finite. We now allow Ni to differ from Ne to see what kind of errors arise in the process, and for this we use the linearized Poisson equation, which is given by epsilon naught del dot E1 equal to epsilon naught k square phi 1 is equal to E into Ni1 minus Ne1. The electron density is given by the linearized Boltzmann relation, which can be written as N1 equal to N naught E phi 1 over kte. We now use this value in the above equation, and then we take common epsilon naught phi 1, and then the final equation will become epsilon naught phi 1 into k square plus n naught e square over epsilon naught kte, which is equal to Eni1. Then we replace the value with lambda d, and we get epsilon naught phi 1 into k square lambda d square plus 1 is equal to Eni1 lambda d square. The ion density is given by the linearized ion continuity equation, Ni1 equal to k over omega n naught Vi1. We now use this value of Ni1 into the ion equation of motion. Then we will get iota omega m n naught Vi1 is equal to E n naught iota k over epsilon naught E lambda d square over 1 plus k square lambda d square plus gamma I kti iota k into k over omega n naught Vi1. If we simplify this expression, then we get omega square is equal to k square over capital M n naught E square epsilon naught inverse lambda d square over 1 plus k square lambda d square plus gamma I kti, and further simplifying this we will get the dispersion relation omega over k equal to kte over capital M 1 over 1 plus k square lambda d square plus gamma I kti over capital M to power 1 over 2. This is the same as we obtained previously, except for the factor 1 plus k square lambda d square. Our assumption ni equal to ne has given rise to an error of order k square lambda d square equal to 2 pi lambda d over lambda to power 2. Since lambda d is very small in most experiments, the plasma approximation is valid for all except the shortest wavelength waves. Therefore, we can say that the plasma approximation is valid for all except the shortest wavelength waves. If we assume that k square lambda d square is very greater than 1 and consider the short wavelength waves, then the equation 3 will becomes omega square is equal to k square n naught e square over epsilon naught m k square, and further simplifying it we get n naught e square over epsilon naught capital M, which is equivalent to capital omega p square. We have for simplicity also taken the limit Ti approaches to 0. The here capital P is the capital omega P is the ion plasma frequency. For high frequencies, the ion acoustic wave turns into a constant frequency wave. There is thus a complementary behavior between electron plasma waves and ion acoustic waves. Electron plasma waves are basically constant frequency but become constant velocity at large values of k, and similarly ion acoustic waves are basically constant velocity waves but become constant frequency at large values of k. Summary of lecture number 1. In plasma physics, waves in plasmas are an interconnected set of particles and fields which propagate in a periodically repeating fashion. A plasma is a quasi-neutral electrically conductive fluid, as we know that in the simplest case we know that it is composed of electrons and a single species of positive ions, but sometimes it may also contain multiple ion species including negative ions as well as neutral particles. Due to its electrical conductivity, a plasma couples to electric and magnetic fields. This complex of particles and fields supports a wide variety of wave phenomena. To understand these phenomena of waves or wave behavior, we started our chapter 1 in plasma physics 2 and we started with the representation of waves. Then we studied the group velocity and calculated the formula for group velocity as well as phase velocity. Then we studied the plasma oscillations. After that we studied the electron plasma waves and calculated its expression. Then we reviewed the theory for the sound waves and also we calculated the dispersion relation for ion waves. Then we checked the validity of plasma approximation and found out that plasma approximation is valid for all except the smaller wavelength waves. At the end we obtained or studied the comparison of ion and electron waves. That's the end of our first lecture. Thank you.